So I don't think neural networks need a huge amount of introduction in terms of like what their applications are, because everything, all of the cool stuff that we engage with every day in terms of AI, like self-driving cars, medical image diagnosis, your phone recognizing your face, being able to talk to your Google Assistant or your Siri or your Amazon Echo and actually accomplish things, that's all neural networks. Granted, the advanced versions of them, but at the end of the day, just a neural network. So I want to actually go all the way back to linear regression and talk about a graphical representation for linear regression and then move forward from there. So we've seen many times in linear regression, if we have some like outcome y, we can predict it with some combination, like intercept and then some coefficient times some first feature plus some other coefficient times second feature and on. I think in the first talk I gave, I had the example of like trying to predict the price of a car based on the what did I say? The year it was made, year, and then the miles on the odometer. Just write like odometer. So you'd have some coefficient for that, some coefficient for this, and some intercept term. And then we saw that you can turn this operation here into a pretty straightforward matrix operation. I'm just putting the hat for like that's our estimate. We'd have our data matrix X and then this coefficient B. And then we chose what the best vector of coefficients were, like what the best slopes were for each of these analytically, or we could do it using a gradient-based solver. But I want to redraw this situation in like a graphical format. And graph, I mean like actual graph, like connected nodes. So a way to think about that would be in this function here. Put my pluses in. We have like three features, right? And the features are 1. The next feature is x1, which is the price or the year. Year, I'll put over here. And then we have another feature, x2, which is like number of miles on the odometer. And then we have an outcome that we're trying to predict. And like our mathematical notation would be like y hat, and that's just the price. But feel free to interrupt if you have any questions or anything is unclear. So the graphical representation here is each of these features, we're going to combine them. And I'm drawing these arrows to denote that like we're going to take them and we're going to add them up, but only after we've multiplied each of those features by its respective coefficient, or like a weight. So we're going to take the weighted sum or the weighted combination of these three features. So that is just the same thing as our matrix operation here. If we stored these in a vector, back up here I can write this is just like x times beta, and in here this would also be x times beta. So you take these, you like this times this, this times this, this times this, add them up inside here, and then it spits out the price. And that's linear regression from a graphical perspective. So there's actually there's a useful generalization of linear regression to multiple outputs. And this is actually useful for situations not just trying to explain neural networks. The linear regression is kind of nice because our estimate for the best coefficients to use, we actually have an analytical equation for that, and it's x transpose x inverse x transpose y, where y is the column vector of our actual outputs, like the actual prices that corresponded to each car in our training set. So you could imagine a situation where perhaps you wanted to predict some other continuous outcome. Maybe you also wanted to predict the fuel economy. Maybe that's like y1, and we'd have some other output y2 that we'd want to predict. It turns out that the solution is super easy to do. All you have to do, so let me back up just for a second. In that case, instead of our outcome y being a column vector, it would just be a matrix with 2 columns. The first column would be all the prices, the second column would be all of the fuel economies. So, in a very nice, easy generalization of linear regression, we just replace that lowercase y column vector with uppercase Y matrix. And then, of course, as a result of that operation, you don't get a vector beta, you get a matrix, we'll just call it like uppercase B. And you can, it's another nice, useful thing about this multiple output linear regression is that this situation is actually completely equivalent to just fitting a separate model for each outcome. Because if you work through the math of like how this operation actually works, you'll notice that like the 2 outcomes like don't actually interfere or interact with each other. So that's very useful if you are doing linear regression, you're trying to predict multiple things at a time. And it's also very useful for my purposes because since that is going to be the equivalent of using the same features to predict something else with a different regression model, what I can do is, if you'll allow me to clutter the screen a little bit, I could just copy this whole thing and like paste it down here. But because it's the same features here, what I'm going to do is I'm just going to draw a line like, let me draw it like this down to here. And so we have this other node that's going to spit out the other outcome we care about. So a line going down like this and a line going down like this. So this other model that I've sort of slapped on top of my old one, that is going to have its own set. Maybe I'll call this beta 0, 1, beta 1, 1, beta 2, 1. And these are just the coefficients that you would get if you fit a model just like this, except instead of price, you just put fuel economy. And I'm drawing it in this kind of convoluted networked format for reasons that will become clear. So what we have here is a multiple output. We have like a multivariate linear regression. And the model is graphically represented like this. It's mathematically represented like this. Our outcome y is just x times b. And that matrix B is just 2 columns. One of them is, I was meant to select yellow. So one of those columns is these betas here. I totally meant to give this talk using theta notation because I know that's the standard for machine learning, and I just completely reverted to my statistical roots here. So apologies for that. And then the other column is just the coefficient, these guys, they live over here. So we had a nice analytical solution to this, but that analytical solution was the solution that minimized some cost function, and that cost function was just the mean squared error. Mean squared error. And so that's just the sum of the actual value minus our predicted value squared. It's a mean, so divided by, say, m training examples. And that's averaged over all of the training examples. I did write this correctly, didn't I? Yes. So we had a cost function here. We had a model that we graphically represented like this. That model was parameterized entirely by, number 1, the features we used, and number 2, the coefficients or the weights associated with each of those features. So this is a nice colorful way of looking at linear regression. And we use this for, well, regression problems. And now I want to do pretty much the same thing, but I want to do it for logistic regression, which we saw a few weeks ago. So let's go with the same example, and let's say maybe we wanted to predict not a continuous outcome, but maybe we wanted to predict the probability that a car will break down in the next year. And for simplicity's sake, let's just say it's going to be a function of the year the car was made, and also the number of miles on the odometer. So in this case, it's a very simple generalization of linear regression, except we are, instead of predicting, well, we're going to predict the probability, and we're going to do it like this. We're going to actually, same kind of setup, some intercept plus some coefficient times the year plus some coefficient times the number of miles on the odometer. But we need some like nonlinear transformation to get this, which is going to be a continuous outcome that could range from negative infinity to infinity. We need to bound that between 0 and 1. So we'll use some function, call it g of z. Usually we use the sigmoid function, 1 over 1 plus e to the negative z. And I know we were just griping about poorly hand-drawn graphs, but here we go. So that function looks like this. That g of z, it's just like that. And of course it's 1 and then 0. So this allows us to predict, call it maybe p hat, the predicted probability a car will break down based on these variables. And as you can guess, there's a vectorized version of this, which is just g of x times beta. And this means like apply this function element-wise to everything in the result of this. So let me draw that graphically, and I'll try and keep this, I'll try and keep at least some of these equations on the screen. So same thing, we have 3 features, and the first feature is just a 1. And we have another feature, x1. That's the year the car was made, year. And then we have another feature, x2. That's the number of miles on the odometer. And then this is going to work almost exactly the same way as linear regression. That goes in, that goes in, that goes in, and each of those lines, I know there's a math word for it and I'm completely spacing on it, has a coefficient associated with it, beta 2, and then what happens inside here, in linear regression, we just had x times beta. But now here we're just going to do g of that. We're going to apply that. So we're going to take xb and throw it in right there. And what that's going to spit out is some number between 0 and 1. So it's going to spit out some number, and that number is the predicted probability of breakdown. Car breakdown, break down. And the situation here is a little bit more complicated because we don't have a closed form solution to this, sadly. So we have to choose, choose our coefficients to minimize some cost function, and here we're going to use and I have it written in my notes here, this log loss or cross entropy, which is going to be negative some, and this is, I'm writing the most general case of this where you might have multiple outcomes instead of just one, but of course it'll work for just one. It's y, say we have j examples log, I'm just writing y hat for our estimate. I should keep my notation tight here. So cost. This is very similar to the linear regression situation where we have a model defined by this architecture and the variables we're using. It's parameterized by a set of coefficients, and there's a cost function that we're going to try to minimize to choose the best coefficients for this model. And the difference is that, well, number one, we have to use an iterative method to solve the optimization problem, because there is no general analytical solution for this. And we have this nonlinear transformation happening inside this this little node. So it's like this times this, this times this, this times this, add them up, and then apply some nonlinear transformation. You could actually think about the linear regression situation very similarly, except that we applied a function here, and that function was just the identity function. So we took all these and then we did nothing to them, or we multiplied them by 1. And we can even generalize the logistic regression situation. So everything I've outlined right here is just vanilla, boring logistic regression. I'm going to draw another analogy to trying to predict multiple things at once, or multiple things maybe with the same inputs. So maybe like the first model I drew, we're going to predict probability the car breaks down, and maybe we want some other model using the same features to predict the probability the car gets stolen. Some other 0, 1 outcome. And I can do a similar thing where if I'm using the same input variables, I can draw, again, forgive me for cluttering the screen here, but draw a different logistic model like this. And each of these, so it's the same input variables, but because we're trying to predict something different, obviously the coefficients we're going to use are going to be different. Beta 2. So same thing, we're going to take in here, we're going to do the same operation of x, except it'll be, I mean, I'll just call it like beta prime, because it's a different model. And then we're going to do g of that. So we could fit this model separately by minimizing a cost function, choosing the best set of coefficients for this model that I'm drawing in pink, and then we'd be predicting two things at the same time. Now, I want to recall, like I'm writing like, you know, predicting probability of something, but what's actually, I mean, what's coming out of these models is just a number between 0 and 1. So you can have a situation where, like, okay, maybe you put your variables in, you predict the probability the car breaks down is like 0.3, and you fit this equation, you predict the probability that the car gets stolen is like 0.1. And then the big insight here, where the magic happens is saying, okay, I have a number right here, and I've got another number right here, and I can do a lot of things with numbers, but one thing I can do with numbers is I can put them into regression equations and get an output. So I could just tack on another, let's just say it's another logistic regression unit over here, and let's not forget our intercept. Always want an intercept. So I've just drawn a different model here, parameterized by some other set of coefficients. Maybe I'll call it prime prime. I know I'm being sloppy with my notation here, but that's what you get when you aren't a math major. And this is going to spit out some number between 0 and 1. Now, this seems like kind of a crazy idea. Why would you do this? But let's recall one of the properties of plain old-fashioned logistic regression, like I had drawn. What? Sorry, yeah, it should be between 0 and 1. Should be, because it's like it's going into the sigmoid function, so it's like this is going into that, and so it's going to spit out something. What's the right way to write that? Is it? Okay, it was. Okay. All right. Is that right? This. All right. Good. Yeah, can I kick the can down the road on how to choose those parameters for a few minutes? Allow me a little bit of a leeway here, because you're completely right. I'm dodging the minimization issue for the time being. Ignore the complicated version of this. Regular logistic regression, normal run-of-the-mill logistic regression, has the property of being it's like a linear classifier, assuming we don't add polynomial features or something. So what that means is that if you have two classes like this, logistic regression is going to draw a line between them, and that's just a function of the fact that's a function of this being a linear operation right here. So the motivation behind why do this, why stack two models on top of each other, and why introduce these interdependencies is as follows. And this is like the core magic behind a neural network, because that's what I drew here. I just sort of sneakily created one on the fly. The core magic is that if you take linear combinations of the outputs of nonlinear functions, you can learn a nonlinear hypothesis. So this crazy model I drew here, it has one output, and it's going to predict just one probability, but in principle at least, this kind of model is capable of learning nonlinear decision boundaries. So it might be able to do something like this if we had more data over here. So that the key motivation is taking combinations of multiple nonlinear transformations. If you try doing this with just the identity function as your g of z, it wouldn't work, because you could all prove this on the back of an envelope. Any linear combination of linear combinations is a linear combination. So one thing I like this way of presenting neural networks a lot, because it's makes it look like a straightforward generalization of logistic regression, but I think it maybe obscures an important fact, which is that it makes it seem like there's something special about the sigmoid function, when in truth, to get out of linearity, you really don't need much. You can use, well, you can't use any nonlinear function, but you can use some pretty boring and simple ones. In fact, you can even use the most simple nonlinear function you can think of, which is this one. This is like, if you wanted to think of like the most contrived, stupid nonlinear function in the world, it would be this. But it turns out that if you take this function, of course, because it's so stupid, we have to have like a cool sounding name for it. It's called the restricted linear unit, or ReLU function. If you go back up here, and instead of doing sigmoid, if you just do that, if you make your g of z this, this all works just as well. You can get really impressive performance, and actually quite often better performance for some technical reasons, out of a very simple, very straightforward nonlinear function like this. So with regards to some of the pieces I've been avoiding right now, or for now, let me like redraw a simplified version of that network I had up there. So what do we have with this example we've been going with? We've got some set of models, and well, we have a network, we have an architecture, just like we had with the linear regression and the logistic regression examples. We have this like architecture of nodes, and we have a couple input variables, and this network is going to be parameterized by each of the coefficients associated with the lines. So because neural networks are usually the letter theta as opposed to beta, maybe let me switch my notation here. This and oh, I missed one line, didn't I? Oh, no, I didn't. So those two, maybe that's got some theta, that's got some theta, and these nodes have some associated thetas, and these also have some associated theta. The point is, you can store all of those in a matrix, just like I did with my linear regression example, call it capital theta. And then over here, you could store all of these in some other matrix. In this particular case, it would just happen to have one column. But you could imagine me generalizing this by adding more nodes. And those coefficients could also live in some other matrix, call it, I don't know, 1 and 2. So I have a set of input variables, I have an architecture, and I'm like parameterizing my model by the coefficients. And I choose those coefficients by minimizing a cost function. So that's going to be another thing I need to like specify in the design process. In this case of like predicting some output, you could use the same log loss or cross entropy, which I wrote up earlier, or if we wanted to do like just like a regression type situation, we could use mean squared error. So in principle, the idea is really similar to linear or logistic regression. We have a set of parameters, we want to choose the best parameter, and we specify what is the best by some cost function. So either log loss or mean squared error. And I'm a visual person, so I quite like these visual depictions. But another way of thinking about this is as a really simple, like one-line kind of math situation. Each of these, like each of these, well, they're called, I might as well use the correct terminology. They're called layers here. These layers have an associated function that happens inside here. So we take our x theta and we do some function, some nonlinear function to it. In the example I gave earlier, that was the sigmoid function. When I was talking about this situation, that was the ReLU function. The technical term for this is the activation function. So that's associated with each set of nodes. As you might imagine, if we were doing a regression problem, this final node here, we would want to use we would not want to use the sigmoid activation function because we'd want to output some real number as opposed to something bounded by 0 and 1. The idea is we need to choose these inputs by minimizing a cost function. And it becomes more difficult to do so because they are now like interrelated. So changing this number affects also like the effects of the weights of this part of the network. So we were going to talk about not the complicated picture version of this, but the math equation version of the neural network. If you have some piece of data, xi, as like a vector, it goes in, and it's pretty simple, right? We're just going to do xi times this first theta, and then we're going to do, definitely going to run out of room here. Then we're going to do g of that. And then we're going to take that and we're going to multiply it by the second matrix. And then we're going to do g of that. And that gives us our predicted outcome. And as you could imagine, this generalizes magnificently well, regardless of how many nodes there are in each layer, regardless of how many layers there are, regardless of how many outputs you are, because then this lowercase y would just become uppercase y, which is really quite nice. While it's very slow to train neural networks, it's relatively fast to make predictions with them, because if you're a mathematician, you probably appreciate this simplified version as opposed to this big graphical version. So how are we going to minimize this cost function? What we need is the partial derivative. Let me call this cost function c. Cost function c. We need like the partial derivative of the cost function with respect to what? Well, we need the partial derivative with respect to like every single element of every single matrix here. So what would it be? It'd be like theta I j k for like the ith row, jth column of the kth layer of the matrix. So if we could do that, that equals some vector in I times j times k dimensions, some big vector, and then we get this somehow, and then we can just do gradient descent. So just like update, update theta I j k using some small step times the negative of the partial derivative. And there's an additional complication to this beyond how do we get that partial derivative, and that complication is this. Linear regression and logistic regression have the very nice property of being convex functions. So for linear regression, if you did linear regression with just one variable, say you mean centered your y so you didn't have to worry about an intercept, that cost function is just like a roll. You can do gradient descent, and once you get to the bottom, you're at the bottom. And logistic regression, even though we can't write out an analytical solution, somebody smart somewhere proved that the logistic regression cost equation is also convex. So once our iterative solver converges, we get to the bottom, we know we're at the global minimum. Unfortunately, for neural networks, the cost function is not necessarily convex. So of course the cost function actually exists in many, many dimensions, but if it were in 1D, you could in principle get stuck here, or you could have a situation where maybe you think you're at a local minimum, but you're not at all. And dealing with this has to do with a lot of the kind of like practical like tips and like more of the art as opposed to the science. Like how do you engineer a gradient-based solver to kind of like roll up and out of this hill and keep going down? How do you make sure you don't overfit? So on. So if you'll excuse me, I will actually not talk about how to get this partial derivative, because honestly I think it would take me well over an hour just to talk about that. At least for me, it's something that I find quite challenging. But it's essentially, so the term for doing this, the procedure, is called backpropagation. And it has a lot to do with applying the chain rule for derivatives to the written out math version of this. So what you have to do is you have to compute the partial derivative for each element of the set of parameters that define the neural network, and you have to average that across all of your training examples. So this is why when you hear about like people training neural networks for weeks, this is why, because you have I times j times k elements in here, and you have to compute those for each of your training examples each time you take a step, and you have to take many, many steps to actually optimize the equation. So backpropagation is the procedure by which this fitting happens. And the reason I was being a little hand-wavy earlier about choosing the best parameters for logistic and linear regression is that, at least from a 10,000 foot perspective, it's the same idea. We're going to try to choose the best, or as well as we can get, parameters for the network that minimize the cost function. So I would be remiss as somebody in the human performance program not to talk a little bit about some of the biological inspiration for neural networks. And so I have here a drawing I copied from Wikipedia of a biological neuron. And you have trillions and trillions of these in your brain and throughout your body. And they have a couple different pieces. Well, maybe I should ask, before I go off on this biology tangent to avoid having to talk about backpropagation, are any questions about this whole situation over here with the mechanics of it? No? Okay. All right, I will continue then. So, okay, in a biological neuron, you have a big piece up here. It's called the soma. It's like my favorite coffee shop here. It's called the soma, and that receives like input from maybe other neurons, maybe like other like stimuli from your body. So like in your fingers, you have nerve endings that are sensitive to pressure. You have nerve endings that are sensitive to heat. And when these little, they're called dendrites, these little like branches of the soma, when these dendrites receive some stimulus or some input, they release some neurotransmitters inside the neuron, and that builds up electrochemical potential. And if it just receives a little bit of an input, that electrochemical potential builds up, but then it kind of peters out. So if you like made a little graph of the potential, it like maybe like some stimulus, and then it just kind of peters out. But if they receive a very large stimulus, so for example, if you go to grab a pot on the stove and it's really hot, your heat-sensitive neurons in your fingers get a huge stimulus, and what happens is that there's this threshold effect up here, and that if the electrochemical potential inside the neuron gets above that, it's called an activation potential, the neuron fires. It's just like pulling a trigger. It's why it's called a neuron firing. And what happens then is there's this electrochemical chain reaction that propagates down the length of this long little arm called an axon. So it has to do with sodium flowing out of a channel and potassium flowing into a channel, and that action potential, it's called, goes all the way down here to the end, the synapse, or it's called the axon terminal down here. And what happens then is then neurotransmitters get released out of the ends of the axon terminal into the area called the synapse. And that is significant because quite often at the other end there is another neuron, or the dendrites of another biological neuron over here. And so they receive an input. If that input is strong enough, then it activates that neuron, and chain reaction propagates down, blah, 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 blah. So while this was some jolly interesting biology, it is also, maybe you saw the intuitive connection here with, if I made a graph of input and then output. So like input, meaning like the stimulus going into the neuron over here. Output, meaning the like electrochemical potential that goes down the length of the neuron. The graph looks like this. Well, if the input is too low, nothing, 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 and then once it crosses a threshold, then it goes up. This looks awfully familiar, right? So this is that looks just like our ReLU function. Or you could imagine it like a sigmoid if it's no input and then a certain amount of output. In any case, this is sort of the like biological inspiration for a neural network. I don't want this to be interpreted as me saying artificial neural networks are biological neural networks, because there's a lot more going on in biological neural networks that we just completely ignore with artificial neural networks. But I like this connection here, and it gives you some intuition on why this kind of mathematical setup actually works to learn complex nonlinear hypotheses. There are structural circuits in the brain that seem to perform some of the same functions that complex artificial neural networks perform on the same task. So, for example, one task that artificial neural networks are particularly good at is recognizing images. And if you want to recognize an image that's been like partially obscured, one very good type of neural network that can do that is called a recurrent neural network. And that works essentially by taking output and like shoving it back into the network earlier. And it appears, at least according to some research, that there are similar recurrent neural structures in the brain where signals kind of further down the chain get passed back into the same structure again. So it's like a nice sort of up in the clouds similarity between the networks that we build and the kind of neural networks that we are built of. So in my notes here, I had some, I wanted to like kind of give a pencil and paper proof of neural networks learning nonlinear hypotheses, but then I just found this super great thing, which is a web app built by the people who made TensorFlow, which is one of the really popular neural network. I don't know, it's not a programming language, but it's like a, what would you call it, a toolkit? So what it's really great at doing is showing you how neural networks learn nonlinear hypotheses. So I have right here set up just like what I've been drawing on my little blackboard here. I have two features, x1 and x2. I've got a single layer of, it's called a hidden layer with two neurons. And what you'll notice is that if I increase the complexity of the network, say by adding additional neurons to it, this network becomes able to learn more complex hypotheses. The same is true if you add additional layers to the network. Another thing this tool is great at is some of the tips and tricks and art of a neural network. I think the problem I have, let me try this. Yeah, here we go. Okay, so this is you can see my cost function here is not quite converging. But this is a fun thing to play around with. And the thing I switched up here, and the reason why these, this is another thing I wanted to talk about anyways, the reason why people use this ReLU function here is because of exactly what you were seeing right here. Let me see if I can replicate that. So you'll notice, oh shoot, it's working now. Sorry. However I had it set up earlier, let's try this. Oh, it looks like this is going to work as well. Well, what can happen with sigmoid functions is that if you're stuck way out on either end of the function, like way, way, way off to the right or way, way, way off to the left, you can imagine that the gradient there is almost zero, right? It's super, super shallow. So it's called like a vanishing gradient problem. So one of the nice things about this ReLU function is that it is less prone to that problem. Okay. I've been talking a lot about neural networks for classification, but I do want to emphasize that if we want to do a regression problem, like if we want to predict one or in fact many outcomes that are continuous, you can use mean squared error and it works just fine. There's a really nice little mathematical trick where the way you compute the gradient using backpropagation is almost identical. You'd think that like if you change out your cost function, it would change the gradient, which it does. But there's kind of like a nice mathematical trick with mean squared error and cross entropy where the partial derivatives are quite similar in terms of how they shake out in backpropagation. So actually some of the word research I'm hoping to use neural networks for are more regression type equations. What's the stock market going to be tomorrow? What generating an image or a video? I think maybe it's a mean squared error type situation. One final piece related to the cost function that I do want to talk about to wrap things up. Mean squared error, let's go with that. Let's say we're fitting a regression model with the neural net, or with anything, any kind of function. Mean squared error is the actual value minus our prediction for that value squared. And when we minimize this cost function, we get some parameters for our model, whether that model is linear regression or whether that model is a neural network. If we want to prevent overfitting, this was actually the topic of the previous talk I gave for this seminar, we can add something to the cost function. We can say add some penalty for each coefficient. And I guess if this is a neural network, well, let me just say, let's set this up for like simple linear regression first. You can say add a penalty where I want to square the magnitude, like I want to square each coefficient and add this penalty, some small number. So greater than or equal to 0. So what you can imagine is what this would do is it would tend to shrink the size of your coefficients here. And several weeks ago I showed how you can use this for fitting smooth nonlinear functions. We use this in linear regression for, this is called ridge regression. You can do exactly the same thing in a neural network. The only difference, of course, is that it's like a triple sum. But basically, you just need to add up put like a penalty on each of the parameters of the neural network, and you can use this lambda here, the regularization term, to control how complex the model gets. And that's actually one of the options over here. If you want to use regularization, you can select a penalty. So this squaring the magnitude, it's a L2 penalty. You could also take the absolute value, and that's called an L1 penalty. You probably know that. There's another form of regularizing neural networks that does not have an analogy for more simple models. It's called dropout. And I actually don't know a huge amount of like the technical details on how that works, but essentially as you are optimizing your cost function, you will just randomly kill off a neuron, just like delete it, with the idea being that will discourage the network from learning representations of the data that require many, many, many neurons connected together, which apparently, I'm told, helps with controlling overfitting. So this was a little bit of a kind of a wild dance around all the possible different situations involved in a neural network. But I think maybe the key insight is that taking linear combinations of nonlinear functions and then doing a nonlinear function to those combinations, that is kind of the engine behind the magic of a neural network. And that's why your phone can learn extremely nonlinear hypotheses like, is this face in front of me you or somebody else? Or like if I'm driving down the road, which way should I turn? Or even what is being written on a blackboard in front of me. One of the coolest AI experiences I've had in the last few years was some high schoolers showing me an app that apparently can take an equation that you write out like in handwritten form like this and then solve it and show you how to solve it. So that's a very nonlinear hypothesis, but it's something neural networks can do. Hopefully you found this helpful and at least give you some intuitions on what neural networks can do and give you some jumping off points for learning more about how to actually implement them or understand what they're trying to do.